Hello everyone. Today we will discuss chapter 4 or chapter 10 in the textbook. The title is Refrigeration and Heat Pump Systems. You will see that there are a lot of mechanical components outside there that rely on this refrigeration and heat pump principle. Therefore, this topic is also one of the topics offered by mechanical engineering at the UTSA as an elective course. So you can check that one of the elective course is the refrigeration and heat pump system. This is the learning outcomes of this chapter. First is to demonstrate understanding of basic vapor compression refrigeration and heat pump systems, and then to develop and analyze thermodynamic models of vapor compression systems and their modification, including sketching, schematic, and accompanying TS diagram. So we will use TS diagram again in this chapter. And then evaluating property data at principal states of the systems. And then applying mass, energy, and entropy balance for the basic processes. And then determining refrigeration and heat pump system performance, coefficient of performance. So this is the parameter that will be used to estimate or to quantify the performance of the refrigeration and heat pump system. And then the capacity. The next one is to explain the effects on vapor compression system performance of varying key parameters. And then the last one is to demonstrate understanding of the operating principles of the absorption and gas refrigeration system and perform thermodynamic analysis of gas systems. So some of these learning outcomes are the same as the one in Thermo 1. So you will see some of the topic has been discussed in Thermo 1, and we will have a quick review on this Thermo 2. So that we have a good continuation with the additional chapter discussed in Thermo 2. This is the content of this chapter. The first topic will be vapor refrigeration system, and then analyzing vapor compression refrigeration system, and then we will talk about the refrigerant. So this is the working fluid of this refrigeration system. In daily speaking, usually people call this as a Freon, so F-R-E-O-N. And then the next one is absorption refrigeration, and then gas refrigeration system, and the last topic is heat pump systems. The first topic is vapor refrigeration systems. The purpose of a refrigeration system is to maintain a cold region at a temperature below the temperature of its surrounding. In daily speaking, you call this AC, air conditioning. It's also a refrigerator. So in this case, you want to keep the space inside the refrigerator cooler than the environment temperature. So it's when you place your refrigerator at the kitchen, so it's mean you want to have the room inside the refrigerator be cooler than the temperature of the kitchen room. Or it is AC, so AC installed in our house, so you want to keep the living room, any room inside the house, be cooler than the temperature outside of the house. Okay, so the first one that you would like to see here is the ideal cycle for the refrigeration system. So in this case, it's called Cardinal refrigeration cycle. There are four main components in this Cardinal refrigeration cycle. The first component, it's called evaporator. So inside this evaporator, the refrigerant or the working fluid receive a Q in from the region that we are cooling. So either this is the room inside the refrigerator or the living room in our house. Okay, there will be a Q in going into the working fluid that change the state from point number 4 here going to point number 1. Okay, And looking at this feature, that the temperature of this region is Tc, okay? And in this Carnot refrigeration cycle, we assume that the heat transfer occurs reversibly. So it's mean we don't need to have delta T between the region temperature and the working fluid temperature. Okay, and therefore you can see in this TS diagram, Tc is the temperature of the room that we cool, and then the temperature of the refrigerant inside the evaporator is also at Tc. So see here, so point number 4 has the same temperature as point number 1, and they equal to Tc. Why? Because the heat transfer for this Carnot refrigeration cycle occurs reversibly. Okay, so we don't need to have delta T here. And then from point number 1, the working fluid is directed to the compressor. So there will be a compression process that changes the state 1 to state number 2. Okay, because there is a compression process, so it's mean the pressure at point 2 is higher than the pressure at point 1. So you can also see clearly here in the TS diagram. So in Thermo 1, I believe you learn about the constant pressure line in the TS diagram. So this is this one. This is the constant pressure line. So it's mean here point 1 has the same pressure as point 4, and then this is another constant pressure line. So let's see, here is P1, this is P2. So P2 sure is higher than P1. And then at point 2, the pressure is higher, temperature is higher than point 1. Then the working fluid is directed to the condenser. So inside the condenser, there will be a heat transfer from the working fluid into the warm region. Okay, and the warm region temperature is TH. Okay, TH. And like inside the evaporator, the heat transfer occurring in this Carnot refrigeration cycle is a reversible process. So it's mean we don't need to have a delta T between the working fluid temperature and the warm region temperature. So the working fluid temperature and the warm region temperature is TH. Okay, so there'll be a heat transfer from the working fluid that change state 2 to state 3. So in the TS diagram, you see that state 2 is at saturated vapor. Okay, this is saturated vapor at the dome line on the right side, and then state 3 is at the saturated liquid. So this is at the dome line on the left side. Okay, there is a heat transfer out of the working fluid, therefore the enthalpy, so this is an open system, so we will use enthalpy when analyzing the system. So because there is a heat transfer inside the condenser, the enthalpy decreases from the one at state 2 to state 3. Okay, and then to bring this state 3 back to state 4, so that we have a cycle process here, we have a turbine here. So inside the turbine there will be an expansion and produce work, and this change state 3 back to state 4. Okay, so this is the basic principle of the refrigeration cycle. In this case, this is the ideal refrigeration cycle. It's called Carnot refrigeration cycle. And in this Carnot refrigeration cycle, you can see that it has 4 processes. Okay, 2 processes are a constant pressure processes. So this is the process from point 4 to point 1 inside the evaporator, so no pressure drop. And then the process inside the condenser that changes state 2 to state 3, this is also a constant pressure processes. The other 2 processes are isentropic processes. So it's mean the entropy stay the same. This is the compression process that changes state 1 to state 2. So you can see this TS diagram that S1 equal to S2. Okay, the second isentropic process is the expansion process inside the turbine, and you can see in the TS diagram that S3 equal to S4. So the compressor will require a work here. So this is that we will need to pay. So if it is your refrigerator, you need to pay the electricity to propel this compressor. And in this Cardinal refrigeration cycle, we have a turbine component here, and for sure the turbine will produce some work. So W dot T here. The next one is looking at the performance of the Carnot refrigeration cycle. So in the gas Brayton cycle or Otto cycle, diesel cycle, we have a parameter called thermal efficiency. So in this Carnot refrigeration cycle, we also have a parameter to quantify the performance of the system, and it is called coefficient of performance or COP. So the way it is estimated, the same as the way we estimate the thermal efficiency of the previous cycles. So it is the ratio of what we gain, so what gives us a benefit here, over what we pay. So in this refrigeration cycle case, what we gain, what gives us a benefit is the Q in. So the heat that is taken from our living room or the heat that is taken from the food inside the refrigerator. So this is Q in. So this is what we gain, and in this case we have the formula as per unit of mass flowing. So this is Q dot in over M dot, and what we pay is the energy required to propel the compressor. And in this Carnot refrigeration cycle, we also have a turbine, and turbine produces work. So in this case, what we need to pay is the net work. So this is the compressor work minus the turbine work. Okay, so W dot C over M dot minus W dot T over M dot. And by looking at the TS diagram, a Q dot in over M dot here is the area surrounded by point 1, okay, and point 1, and then A, and then B, and then 4, and then back to 1 again. So if we put a color or a pattern here, so this is the Q in, okay, this is the Q in, and then the network here is actually the net Q as well. So Q in is shown in this figure, the pattern with the yellow line, and then the Q out, this is the heat transfer that is removed from the working fluid, and this happened inside the condenser, is the area represented by point 2. Okay, let's use different color. Point 2, and then point A, point B, point 3, and back again to point 2. So this is the area represent the Q dot out over M dot, and the difference between Q dot out and the Q dot in is the area enclosed by point 1, 2, 3, 4, back to 1. Okay, so this is what we pay. Okay, this is what we pay. So the coefficient of performance represented by beta here, and we call this beta max because this is the ideal cycle, because this is the Carnot cycle. This is the ratio between Q dot in over net work. Okay, so this is the area patterned by this yellow line over the area patterned by this red line. So this is a process that occurs isentropic and the process that occurs at constant pressure. You can also use the area here to represent the Q in and Q out, as well as Q out minus Q in, and then you can replace, or you can formulate the area by this formula. So Q dot in over M dot here is TC, okay, TC times SA minus SB, okay, SA minus SB. So, and this is the area represented by this yellow line. And then the parameter in the denominator, so this is TH minus TC times SA minus SB. This is the area represented by this red line. Okay, and we can simplify this formula to get equation 10.1. So beta max equals to TC over TH minus 1. Okay, so once again, this beta max represents the maximum theoretical coefficient of performance of any refrigeration cycle operating between regions at TC and TH. Once again, any refrigeration cycle that operate between region at TC and TH will have coefficient of performance of beta max. Okay, we have a look at the ideal Cardinal cycle of this refrigeration system. Now we are looking at the departures from the Cardinal cycle. Let me write it down again, the formula of the beta max here. So beta max equal to TC over TH minus TC. Okay, for having a reversible heat transfer, we don't need to have a delta T, but we will need an infinite area for this heat transfer. So in reality, so this won't happen. So it means we will need a delta T to enable this heat transfer because the area is not infinite. So the first departure is that the heat transfer between the refrigerants and the two regions, so it's cold and hot regions, are not accomplished reversibly. So look at this TS diagram. So to enable the heat transfer from the working fluid to the cooled region, so this cooled region, either the room inside the refrigerator or our living room that it's cool during the summer season. So the working fluid temperature must be lower than the cooled region temperature. So if our region temperature, the cold region temperature is TC, so the working fluid temperature must be lower than TC. So in this TS diagram, it is represented by this TC prime. Okay. So similarly, if we want to have a heat transfer from the working fluid to the warm region, the working fluid temperature must be higher than the warm region temperature. So if the warm region temperature is TH, the working fluid temperature must be higher than TH, and in this TH diagram it is represented by TH prime. Okay, so this will enable the heat transfer from the cooled region to the working fluid, and in this one it will be heat transfer from the refrigerant or from the working fluid to the warm temperature. So with this departure, then we have a coefficient of performance formula, and this is represented by this beta prime. So similar to the formula of the beta max, so this is the area that represents Q dot in over M dot to the area representing the W net over M dot. And you can see in this formula 10.2, the beta primes is the ratio of TC prime over TH prime minus TC prime. And you can see from this TS diagram that TC prime is lower than TC, and then TH prime is higher than TH. So first looking at the condition of TC prime lower than TC. By looking at this formula 10.2 or this formula, this is 10.1, as we lower TC, beta max decreases. So this will have a worse effect to the performance of the system. And then the second one, TH prime is higher than TH. So you can see again to this Betamax formula. As we increase TH, the Betamax decreases. So these two departure make the Betamax decreases. So therefore, now you have the parameter of the beta prime here. It is not maximum anymore, okay, because of this departure, two departure here. The next one is that the presence of liquid droplet in the flowing liquid vapor mixture can damage the compressor. So in a real application, we avoid this condition. So this means that we need to push this 0.1 prime more to the right side. So either it is at this saturated vapor or somewhere here, okay, at the superheated vapor. Why? Once again, if we have a liquid entering the compressor, it will damage the impeller or the blade of the compressor and thus shorten the lifetime of the compressor. Okay, therefore in real application, this 0.1 prime is at minimum is at the saturated vapor. Okay. Okay, number 3 is that it is impractical to have the expansion process from the saturated liquid. Yes, we get some work from this expansion process, but the amount of the work is very small. Therefore, in real application, we sacrifice this small work, okay, and replace the turbine by an expansion valve. We don't get any work from this expansion valve, but the price is much cheaper than the turbine price, and the maintenance of this expansion valve is also cheaper than the turbine maintenance. Therefore, in a real refrigeration cycle, we have this configuration. So we don't have a turbine as the component of this refrigeration cycle, rather this turbine is replaced by expansion valve. Okay, so we have this refrigeration system now consisting of evaporator and then compressor and condenser, and the last component is expansion valve. And then also the phase at 0.1 entering the compressor is either saturated or superheated vapor. So it means we have 100% vapor. Because of this condition, usually it is also called vapor compression refrigeration systems. Okay, the next parameter that we need to quantify is the heat transfer from the refrigerated space. It is Q dot in over M dot. In this case, it is formulated as the enthalpy difference between state 1 and state 4, equation 10.3. Like in the previous analysis for a vapor power system and then Brayton system, we use a positive number here to avoid confusion. So Q dot in over M dot here is H1 minus H4. And this Q dot in is also called refrigeration capacity. So for you who has experienced purchasing a refrigerator in the past, one of the questions when you go to Best Buy or Walmart or any shop is, what is the refrigeration capacity? And the unit is either it is kilowatt or BTU per hours, or this is the common unit. So I believe people in the refrigeration system area use this unit, ton of refrigeration. So if you go purchasing this refrigerator, the question is, how many tons do you want to have? So half tons, 1 tons, or 2 tons. So, and 1 ton of refrigeration here equals to 200 BTU per minute, or it is about here 211 kilojoule per minute. The next parameter is the compressor work. Okay, so we know compressor required work, and there will be a work from outside going into the system, but we, once again, we want to have a positive number in the analysis. Therefore, we use this formula 10.4 to calculate the compressor work. So this is H2 minus H1. Okay, so it's positive. And then the heat transfer within the condenser, equation 10.5. So this is H2 minus H3. Okay, this is also a positive number there. But in the exam, I'm okay if you want to use a negative number as long as it is consistent. Okay, the next one for the throttling process inside the expansion valve that changed state 3 to state 4. So in this throttling process, the enthalpy values stay the same. So therefore H4 equals to H3, equation 10.6. And then the coefficient of performance of the vapor compression refrigerant system is formulated by equation 10.7. So beta equal to Q dot in over M dot, and then in the denominator we have WC dot over M dot, and this is H1 minus H4 over H2 minus H1. So you can see in here when we are analyzing a vapor compression refrigerant system, so the first step is to fix the properties at each state, at each operating point here, point 1 through point 4. So once we get the enthalpy at each point, we can start calculating Q dot in, WC, and then Q dot out, and finally in the beta here. These are the assumptions that we have on the ideal vapor compression systems. The first assumption is that there are no frictional pressure drops and the refrigerant flows at constant pressure through the two heat exchanger. So you can see in the TS diagram that this is a constant pressure line. So therefore P4 equal to P1. So there is no pressure drop inside the evaporator. The second one is this one. So in this case P3 equal to P2S. So there is no pressure drop inside the condenser. And the next one is if compression occurs without irreversibilities and heat transfer to the surrounding is also ignored, this means that the compression process is isentropic. So therefore we have a straight vertical line connecting state 1 to state 2S. Once again, if there is no irreversibility, but in case we have irreversibility, then you will have a dashed line here going to the right of the current solid line. Okay, let's have a look on this example. Refrigerant 134A is the working fluid in an ideal vapor compression refrigeration cycle that communicates thermally with a cold region at 0 degrees C and a warm region at 26 degrees C. Saturated vapor enters the compressor at 0 degrees C, and saturated liquid leaves the condenser at 26 degrees C. The mass flow rate of the refrigerant is 0.08 kg per second. The first question is the compressor power in kilowatt, and then the next one is the refrigeration capacity in tons, and then the coefficient of performance, COP, and then the coefficient of performance of a Cardinal refrigeration cycle operating between warm and cold region at 26 and 0 degrees C respectively. Okay, let's take a look on the solution of this example. On the left side is the schematic of the system. So it has evaporator and then compressor and then condenser and expansion valve. And then point 1 is at the compressor entrance, and then point 2 S here, exit of the compressor. This is isentropic process, so we have 2S. And then point 3 is at the exit of the condenser or the entrance of the expansion valve. And then point 4 here is at the exit of the expansion valve. And then the TS diagram is on the right side here. We have point 1 it is mentioned in the problem statement that point 1 is at the saturated vapor, so it is right at the dome line, and then it is connected to point 2s straight vertical line because it's isentropic process, so S1 equal to S2s. And then point 3, it is also mentioned in the problem statement at saturated liquid, so it is at the dome line on the left side. And then expansion process inside the expansion valve, so this maintain the same enthalpy, and this is an irreversible process, therefore it is a dashed line here connecting state 3 to state 4. Okay, and then this is the list of the engineering model. So in the exam I suggest you to put this assumption or engineering model. So the first one is that each component is a control volume, so it's open system at steady state. Okay, and then except for the expansion through the valve, which is a throttling process, and then this is irreversible process. All processes of the refrigerants are internally reversible. So this is inside the evaporator, inside the compressor, inside the condenser, and so on. And then number 3 is that the compressor and expansion valve operates adiabatically. So for the one inside the compressor, when you combine this assumption number 3 with the assumption number 2, this means that the process of the compression is isentropic process. And then number 4, we can ignore the effect of the kinetic and potential energy change. And number 5, as I mentioned, that saturated vapor enter the compressor, so it's point number 1, and then saturated liquid leaves the condenser. This is state number 3. And then the first step, for sure, we need to fix the properties at each point. Okay, so from the TS diagram, so it is shown at the bottom here, point number 1, so this is saturated vapor. Okay, saturated vapor, and the working fluid is R134A, I believe. So it's mean you need to open your table, go to the R134A table, and it is table A10. Okay, go to table A10 and then look at the temperature table. So T1 equal to 0 degrees C. So from the temperature table, look at the Hg. Okay, Hg at 0 degrees C. Then you will get H1 equals to Hg of 247.23 kilojoule per kilogram. And then you need also the information of entropy at state 1 to help us determine the properties at state 2s. Okay, so S1 equal to 0.919 kilojoule per kilogram Kelvin. Okay, and then go to state number 2s here. So this is a superheated condition. So P2s is given in the problem, I believe, or P2s here equal to the saturated pressure at T3. Okay, saturated pressure at T3. Why? The process between point 2s and point 3 are a constant pressure process. So the temperature at point 3 is given, so this is 26 degrees C. So you need to look at what is the saturated pressure at 26 degrees C. So this will be P2s as well. Okay, P2 equal to P set at 26 degrees C, and this is 6.853 bar. Okay, and then the next information, because you need to have two data for the superheated to fix the properties at the superheated. So we have pressure 6.853 bar, and then from this TS diagram you know that S2S equal to S1. Okay, so in this case very probably you need to do an interpolation to get the data at 0.2s. Okay, the pressure is 6.853 bars, and then S to S equal to 0.919. Okay, so looks like you need to do a double interpolation here. So because the pressure number is not a good number, and then entropy number I believe is also not a unique number there. So once you complete the interpolation, you will get H2S of 264.7. Okay. If you still have a problem solving these properties by looking at or by using interpolation or double interpolation, so please have more practice. Okay, review again THERMO 1, where we introduce you firstly about the interpolation process. Okay, so we got H2S, and then we go to state number 3. The temperature is given 26 degrees C, and then state 3 is saturated liquid. So in this case, H3 equal to HF at 26 degrees C. So you use the same table, subtable A10. Okay, table A10, looking at HF at 26 degrees C. So, and the number there will be H3, and you will get 85.75 kilojoule per kilogram. Okay, and then enthalpy at 0.4 equals to enthalpy at 0.3, because this is the process inside the expansion valve. So this is a throttling process. So H4 equal to 85.75 kilojoule per kilogram. Okay, once we complete fixing the properties at each state, then we are ready to answer the question. So the first question is the compressor work input, W dot C. So this is M dot times H2S minus H1. M dot is given in the problem, 0.08 kilogram per second. And then H2S, H1 has been determined, and the equation is in kilowatt, and you don't need to multiply it with any conversion number here, because kilojoule per second is kilowatt. Okay, therefore you have this one is 1 here. So 1 kilowatt equal to 1 kilojoule per second. So the compressor work input is 1.4 kilowatt. Okay, the next one is the refrigeration capacity. So this is Q dot in. Q dot in here equal to M dots times H1 minus H4. Okay, so this equation. So you have all number here, but in this case the unit, the required unit is in ton. So you need to convert from kilojoule per second to be in ton. Okay, to be in ton. So in this case you need to convert from second to minutes. Okay, from per second to per minute. So you multiply it by 60, and this is the conversion from 1 ton, or from kilojoule per minute to ton. So 1 ton equal to 211 kilojoule per minute. And then the next one is the coefficient of performance, or beta. So beta here is Q dot in over WC. So Q dot in, this is H1 minus H4 times M dot, but we don't show M dot here because it's cancelled out between numerator and the denominator. And then WC here is H2S minus H1. So you have all number here, you just plug into this equation, then you will get a beta of 9.24. Okay, the next one is for a Cardinal vapor refrigeration cycle operating at TH 299 Kelvin and TC 273 Kelvin, the coefficient of performance is following this equation, 10.1 equation. So this one is TC over TH minus TC. So if you plug in all this number, you will get a beta max of 10.5. Okay, 10.5. So TH here is 26 degrees C, so you need to convert it to Kelvin unit here. So 26 plus 273, so it is 299. And then TC is 0 degrees C. You convert it to 273 to convert it to the Kelvin unit, so you get 273 Kelvin. So if you plug in the number, you will get beta max of 10.5. So beta max here is the COP of the ideal Cardinal refrigeration cycle. So you have 10.5, and then the beta here, after we include the departure from the ideal cycle, we only have beta of 9.24. The next topic is looking at performance of actual vapor compression systems. The first one is to enable a heat transfer between the cold region and the working fluid. So we need to have a delta T. So in this case, the working fluid temperature must be lower than the cold region temperature, so TC. So this is TC. So you can see in this TS diagram, so the temperature inside the evaporator from the working fluid must be lower than TC. And then similarly, to enable the heat transfer from the working fluid to the warm region that has temperature of TH, so the working fluid temperature must be higher than TH. So this is TH. So this means that T2, T2S, and T3 must be higher than TH. And then the next one, for sure, there is irreversibility or internal irreversibility inside the compressor. So this means that from state 1 in actual system, it is connected by a dash line going to state number 2. Okay, and when it is a solid line going to state 2S, this means there is no internal irreversibility. So because of this internal irreversibility, we have one more parameter here, which is called compressor efficiency, so isentropic efficiency. This is the ratio of the isentropic compression work over the actual compression work. So this is H2S minus H1 over H2 minus H1. And then the next ones, for sure, there is a pressure drop inside the evaporator as well as inside the condenser. But in this THERMO 2 class, we assume that this pressure drop is small or minor. Therefore, we assume that P4 equal to P1. Similarly, P3 equal to P2 or P2S. Okay, let's have a look on the example when we incorporate this deviation from the ideal vapor compression system. So we use the previous example. So refrigerant is 134A, and then the cold region temperature is 0 degrees C, and then the warm region temperature is 26 degrees C, and then the mass of flow rate of the refrigerant is 0.08 kilogram. But in this case, we modify to allow for temperature difference between the refrigerant and the warm as well as the cold region. So in this case, we modify that the saturated vapor enter the compressor at minus 10 degrees C. Okay, why? Because the cold region temperature is 0 degrees C. So to enable the heat transfer from the cold region to the working fluid, the refrigerant or the working fluid temperature must be lower than the cold region temperature. So in this case, we pick up a temperature of minus 10 degrees C. And then saturated liquids leaves the condenser at a pressure of 9 bar. So you will see later on that the saturated temperature at 9 bar is higher than 26 degrees C. Okay, and then the question for this modified vapor compression refrigeration cycle is, what is the compressor work in kilowatt, and then what is the refrigeration capacity in tons, and what is the coefficient of performance. And this is the TS diagram, and then you can see now that the temperature at point 4 and point 1 is at minus 10 degrees C, while the cold region temperature at 0 degrees C. And then the next one, you can see also here that the temperature at point 2S and point 3 is higher than 26 degrees C. So you will see in the next slide what will be the T3, because this is the saturated temperature at 9 bar. And this one is the engineering model or the assumption. So this is a closed system, or sorry, this is a control volume system at steady state, and then except for the process through the expansion valve, which is a throttling process, all processes of the refrigerant are internally reversible, and then the compressor and expansion valve operates adiabatically, and then we can ignore the impact of the kinetic and potential energy change. And then the next assumption is saturated vapor enters the compressor, so this is point 1, and saturated liquid exits the condenser, this is point 3. And then like in the first problem, so we need to fix the properties at each point. So state number 1, so temperature is minus 10 degrees C, so you will need to use table A10. So the refrigerant is 134A, so go to table A10, look at the properties at minus 10 degrees C. So at point 1, this is saturated vapor, so you need to look at the properties for G subscript. So H1 equal to Hg at minus 10 degrees C, so this is 241.35 kilojoule per kilogram, and then S1 is 0.9253 kilojoule per kilogram Kelvin. And then at state number 2S here, pressure is 9 bar, and then S2S equal to S1, and I think you need to do an interpolation. In this case, you need to use table A12, so this is a superheated condition for R134A. So but looks like you need to do only one interpolation. So but you can check whether the data at 9 bar is available. If it does, then you only need to do single interpolation, otherwise you need to do a double interpolation. So once you complete the interpolation process, you will get H2S of 272.39 kilojoule per kilogram. And then state 3, this is saturated liquid at 9 bar, so you use a pressure table. Okay, look at pressure 9 bar, and then HF. So HF here is 99.56 kilojoule per kilogram, and then H4 equal to H3, so it is 99.56 kilojoule per kilogram. Okay, once we completed fixing these properties, then we can start answering the question. The first question is the compressor power input, so W.C, so this is m dot times H2S minus H1. So m dot is 0.08 kilogram per second, and then we got H2S as well as H1. Then you will get the compressor work of 2.48 kilowatt. So you can compare this number with the one from the previous example. And I think this compressor work increases because we have a lower condition at point 1, and then we have higher condition at point 2. And then the refrigeration capacity Q dot in, so use the same method as the previous example. you will get the Q dot in of 3.23 ton. Okay, you can also compare it with the previous example. And then the next one is the coefficient of performance beta. So this is the ratio of Q dot in over W dot C. So this is H1 minus H4 over H2S minus H1. And by plugging all number, you will get beta of 4.57. I believe the previous example has a beta of around 9 point something. Okay, so you can see in here, by introducing the delta T, okay, you can see in here a significant drop of beta from around 9 point, I believe 9.54 to 4.57. So it's half, okay, because half of the performance reduction because of this delta T. Okay, let's take a look on this example. So we use a previous example and then modified it as necessary. So we have refrigerant 134A as the working fluid, and then the modification we put here is that we have a compressor isentropic efficiency of 80%, and then also let the temperature of the liquid leaving the condenser be 30 degrees C. Okay, so T3 is given here, 30 degrees C, and the pressure is 9 bar. Yeah, this one, 9 bar. And then the question is, what is the compressor power in kilowatt? And then the refrigeration capacity in tons, and then the COP. Oh, there is additional question here, the Exergy destruction analysis. And on the left side is the TS diagram. So point number 1, I believe, stayed the same. So this is at minus 10 degrees C, saturated vapor. So this is right at the dome line on the right side. And then, because there is internal irreversibility inside the compressor, so in here we have a dash line connecting point 1 to point 2. Okay. And then we also maintain a solid line here connecting point 1 to point 2S for isentropic condition case. And then P2 equal to 9 bar. And then point 3, you can see here, it has temperature of 30 degrees C. And this 30 degrees C is lower than the saturated temperature at 9 bar. And then we have a throttling process from point 3 to point 4. And this is the engineering model. The first one is each component is a control volume at steady state, and then there are no pressure drops through the evaporator and condenser. And then the compressor efficiency is 80%, so isentropic efficiency. And then the expansion through the valve is a throttling process, and this is an irreversible process. Therefore, the line connecting point 3 to point 4 is a dash line. And a throttling process, it means H3 equal to H4. And then the next one is, we can ignore the effect of the kinetic and potential energy. And then saturated vapor at minus 10 degrees C enter the compressor, so this is point 1. And liquid at 30 degrees C leaves the condenser, this is at point 3. So you can see in here, point 3 is on the left side of the dome. So it means point 3 here is a compressed liquid, 100% liquid. And then for Exergy analysis, we can use a T0 of 299 Kelvin or 26 degrees C. Then the first step, for sure, we need to fix the properties at each point. So point number 1, so we can get the value from the previous example. So point number 1 here is saturated vapor at minus 10 degrees C. So H1 is 241.35 kilojoule per kilogram. So it's the same as the value in the previous example. And then S1 is 0.9253 kilojoule per kilogram Kelvin. Okay, and then we need to do additional effort here to fix the properties at point 2. So we know H2S from the previous example because this is isentropic process. So from the previous example, H2S is 272.39, and then to get the enthalpy at point 2, we need to use this isentropic efficiency correlation. Okay, so the eta here is 80%, and then H1 is 241.35, and then H2S is 272.39. So the only unknown variable here is H2. So we can get H2 from this correlation. This is 80% or 0.8. Okay, so H2 here is 280.15. Okay. Quick check whenever you are doing such a problem in exam and so on. Make sure that your H2 is higher than H2S. Okay, so if because of some reason that you get H2 lower than H2S, you need to recheck again your calculation. Okay, so H2 here is 280.15 kilojoule per kilogram, while H2S is 272.39 kilojoule per kilogram. Okay. So once you get H2, so you can also get S2 as well. Okay, so this you need an interpolation process to get H2, and you use table A12. So this is the superheated table for refrigerant 134A. Okay, and then state 3. So this is in the liquid region. Okay. So in this case, you can approximate this enthalpy at point 3 by using this one. So that H3 is about similar to HF. Okay, here HF at 30 degrees C. Okay, HF at 30 degrees C, and this is 91.49 kilojoule per kilogram. So, and if you want to know where this approximation comes from, look at chapter 3 in thermo 1. Okay, equation 3.14. Okay, you can approximate the enthalpy as the saturated enthalpy at the corresponding temperature. Okay, temperature is 30 degrees C, and then you get HF 91.49 kilojoule per kilogram. And similarly, you can also approximate S3 as SF at 30 degrees C, and this approximation is coming from equation 6.5. Okay, and then from point 3 to point 4, this is a throttling process, so it's mean H4 equal H3, and then you can get the quality of the vapor at point 4 here by using this formula. So this is H4 minus HF4 over Hg4 minus HF4. So the quality at point 4 here is 0.2667. Okay, and then you can calculate S4. And why we need to calculate S4, I believe it will be used to do the Exergy analysis. So S4 you will get of 0.3557 kilojoule per kilogram Kelvin. Once we complete fixing the properties at each state point, then we can answer the question. The first one is the compressor work, so WC dot here. So this is m dot times H2 minus H1. So we have all number here. You just need to plug in, and using your calculator, you will get the compressor work of 3.1 kilowatts. The second question is the refrigeration capacity. So same formula as the one in the previous example. So this is m dot times H1 minus H4. So this is at the exit of the evaporator, and then 0.4 is at the entrance of the evaporator. So you have all number, but make sure that you apply the conversion unit. So first you need to convert the unit of second to minutes, from per second to per minute. So you need to multiply it by 60. And then we know that 1 ton equal to 211 kilojoule per minute. So you will get the refrigeration capacity of 3.41 tons. Question number 3 is the COP beta. So this is Q dot in over compressor work. So H1 minus H4 over H2 minus H1. You plug in all the number, you will get a beta of 3.86. So I remember from the latest example, I believe the beta is around 4.5 something. So you can see here another drop of beta by introducing the internal irreversibility inside the compressor and others. And the next one is the rate of exergy destruction in the compressor and expansion valve. This can be found by reducing the exergy rate balance or by using the relationship of this one. So this is the exergy destruction. This is T0 times sigma of the control volume, and the sigma is the entropy production from the corresponding component. And then with either approach, the rates of exergy destruction for the compressor and valve respectively are formulated by this formula. So this one is for the compressor, and then this one is for the valve. And that's we have got all this number from the previous slide. So we have S1, S2, and then S4, S3. You just plug in the number, you will get the rate of exergy destruction in the compressor. This is 0.58 kilowatt, and then this is the rate of the exergy destruction inside the valve, 0.39 kilowatt. The next one is the pH diagram. So sometimes it is also called Molière diagram. So in this pH diagram, the P is the vertical axis and then H is the horizontal axis. This diagram is the popular diagram used by the people who are working in the refrigeration system area. And most of the time you might not have the table, but the pH diagram is available. Then you will need to use this pH diagram to estimate the enthalpy, entropy, and so on. And you can see in here the unique thing of the pH diagram for the process connecting state 3 to state 4. This is a throttling process, and the enthalpy stay the same. Therefore, we have a straight vertical line connecting point 3 to point 4. And then other points stay the same. And you can see in here the dome line is a bit inclined to the right. Okay, and then you also see a constant entropy line. This is a constant entropy line, and then this line is a constant temperature line. So once again, when you take the elective course of refrigeration system, you will work mostly with this pH diagram. The next topic is refrigerant. In daily speaking, this is also called Freon. Refrigerant is used as the working fluid for the refrigeration system. So there are different type of the refrigerant that can be used for a refrigeration system, and the selection of this refrigerant is based on the performance and then safety and environment impact. The term performance here refers to providing the required cooling or heating capacity reliably and cost effectively. And then safety here refers to avoiding hazards such as toxicity and flammability. And you will see later on that some refrigerants are toxic and others are also flammable. And then environmental impact primarily refers to using refrigerants that do not harm the stratospheric ozone layer or contribute significantly to global climate change. So the last one here is the current issue, so the global climate change. So everyone are working on how to minimize the global climate change. And then it is generally desirable to avoid excessive low pressure in the evaporator and excessive high pressure in the condenser. So first of all, from the performance perspective, when we have a wider pressure range, it means we might need more or higher compressor works. And then if we have excessive low pressure, so the propensity for leaking is higher. And then if we have excessive high pressure, we also have a higher propensity to leaking. And same time, we need to have a special kind of material that is able to sustain or to operate under this high pressure condition. And then other consideration includes chemical stability, and then corrosiveness, and for sure the cost. And then the type of compressors also affect the choice of refrigerant. So when we use a centrifugal compressor, so then they are best suited for low evaporator pressure and refrigerants with a large specific volume at low pressure. And then we can also use reciprocating compressor that perform better over large pressure range and are better to handle low specific volume refrigerant. The next one is refrigerant types and characteristic. Prior to 1930, accidents were prevalent among those who work closely with refrigerant due to the toxicity and flammability of the most refrigerant at the time. And then two classes of synthetic refrigerant, it's called Freon, were developed. So one is from the class of chlorofluorocarbon, CFC, and in this class we have R11, R12, R113, and R114. And then the second class is called hydrochlorofluorocarbon, it's CFC, and in this class we have R22. And then to keep order with so many new refrigerant having complicated name, the R numbering system was established in 1956 by DuPont. So DuPont here is one of the company that are operating in this refrigeration area. And as I mentioned to you, there is an elective course about this refrigeration and heat pump systems. One of the topic will talk about the refrigerant and the rule for naming the refrigerant and so on. And then this table is showing refrigerant including the global warming potential number. So the first column is the refrigerant number, and then the types, whether it is CFC or HCFC. And then the next column is the chemical formula. So like R12 here is a CFC type refrigerant, and the chemical formula is C, so it's carbon, and then Cl, this is chlor, Cl2F2, so Florida. And the global warming potential number is very high here, so 10,900. And then as the reference here, we have a CO2 here with the global warming number or global warming potential number of 1. So it's mean for R12, the potential for global warming is about 10,900 times the one for CO2. And then the next one is R11, and we know that I believe in the US R12 and R11 are not allowed anymore. And then R114, R22 is not allowed also. And then this one is still a popular one, R134. So this is from HFC type class, and this R134 is one of a good refrigerant. However, the price is high, so this is another concern from the refrigeration company. And then the next one here, you can see at the bottom side here we have the refrigerant coming from the type of natural. So I have this explanation in the next slide. So under this natural refrigerant we have carbon dioxide. So when we follow the R naming from DuPont, carbon dioxide name here is R744, and then we have ammonia R717, and then propane, methane, butane. This is the species from natural gas. The next one is environmental consideration. Compelling scientific data indicating that release of chlorine-containing refrigerant into the atmosphere is harmful becomes widely recognized. So there's a concern that focus on release refrigerant depleting the stratospheric ozone layer and contributing to global climate change. And then in 1987, an international agreement was adopted to ban production of certain chlorine-containing refrigerant. So in this case, we have R11, R12, and so on. Then a new class of chlorine-free refrigerant was developed. So this is the HFC, so hydrofluorocarbon. So it means there is no Cl there. And then under this HFC type refrigerant, we have R134A as the primary replacement for R12. And once again, R134A, this one is the allowed refrigerant. However, it costs more money. So although R134A and other HFC refrigerant do not contribute to the atmospheric ozone depletion, they do contribute to global climate change. And then we have another type of the refrigerant here with the CO2. So CO2, it is cheap, and then you can find everywhere. So CO2 R744, and another one is R1234 YF. So this is another type of the refrigerant. Next one is natural refrigerant. So under this type of the refrigerants, we have what is called non-synthetic refrigerant. So CO2, and then ammonia, and then hydrocarbon. So hydrocarbon here is actually a natural gas. So it can be methane or propane or ethane and so on. Non-synthetic refrigerant typically have a low global warming potential. So you can have a look again to the previous table. So ammonia, so R717, serve as a refrigerant for large system used by the food industry and in other industrial application. It's also used in the absorption system. So we will have a dedicated slide about this absorption refrigeration system. And then hydrocarbons such as propane, R290, methane as well, are used worldwide in various refrigeration and air conditioning application, including commercial and household application. And one of the main concern on this hydrocarbon is its flammability. So you know, now there are a lot of research about using natural gas for the engine fuel. So it means it's flammable. It does have a heating value. So when we apply to the refrigeration system, so we must make sure that we don't have any source of ignition that can generate a fire in the refrigeration system using hydrocarbon. We have a look at the vapor compression refrigeration system, and for sure there are other type of vapor compression application, and now we will see on this slide. The first one, what is called a coil storage. So the picture here is showing the schematic, a simple schematic of coil storage. So in this coil storage, chilling water or making ice is conducted during off-peak period. So when off-peak period, this means maybe in the evening, so when the ambient temperature is cooler, and also when the electricity rates is the lowest. So it means we have two benefit here. When the ambient temperature is cooler, so it means we minimize the loss, and in the evening the electricity rate is also the cheapest. So in this simple schematic, we have a refrigeration unit at the top here, and then there will be a cold refrigerant that is circulated to this ice maker, and then inside this one ice will be generated, and then the refrigerant returned back to the refrigeration unit from this line. Okay, and then once again this chilling water or ice making is conducted during off-peak season, and in the daily time we can use this cold ice to do different purposes. For example, we can pump liquid here or with coolant here through this line, okay, and then discharging the heat to this ice storage, and then bringing back the cooled coolant to this tunnel. And then on the other side we have a warm humid air from maybe occupied space, and then remove the heat from this humid air, and then at the exit of this tunnel we have a cool and then less humid air going back to the occupied space. So in this case, because we want to have a less humidity of the air, so very probably inside this tunnel is occupied by a dehumidifier. So it means we lower the water content inside the air. The next one is a cascade cycle. So in this case, we combine two refrigeration cycle with the help of intermediate heat exchanger. So we have cycle A at the bottom here. So this cycle A has a low temperature evaporator and then compressor, and then this one is a condenser side for the cycle A, and then expansion valve. And then the second one is cycle B. In the cycle B, they have evaporator on this side, so, and then compressor, and then high temperature condenser and expansion valve. So in this case we have two compressors, so it means we have two work that need to be supplied to this system. And then a significant feature of this cascade cycle is that the refrigerant in two or more stages can be selected to have advantage evaporator and condenser pressure in the two or more temperature range. So it means you can select a different refrigerant with a different characteristics, so that you can have a different range of temperature as well as the pressure. And then multi-stage compression with intercooling. And you remember in chapter 3 or chapter 9 in textbook that when we apply an intercooling to the compressor, then we can gain some reduction of the compressor work. So we can also apply this idea to this refrigeration system by applying an intercooling during the compression process. And this picture is showing the schematic of this multi-stage compression with intercooling. So we can start from this point, point number 1. So this is at the entrance of the first compressor, and then the working fluid is compressed to state number 2. So in the TS diagram we have state number 1 in this case, and then state number 2. And then before it's entered to the second compressor, the working fluid at the stage number 2 is cooled by the working fluid from the other side, which is 0.9 here, because this 0.9 has a much lower temperature, or has a lower temperature than the temperature at point 2, and then both streams mix inside this direct contact heat exchanger, and then at the exit of this direct contact heat exchanger we have point 3. So at this point 3, the temperature is lower than the one inside the state 2, and then it will go to the second compressor, and then this point 3 is compressed to point number 4. Okay, and then it's enter the condenser, and then at the exit of the condenser we have point number 5, and then it's enter the expansion valve doing a throttling process. It goes to state number 6. Okay, and then the key component here, what is called a flash chamber. So this flash chamber separate liquid and vapor phase. So the liquid phase will be flow to this line. So it's go to state number 7. So state number 7 here is the saturated liquid, and then the vapor part will be directed to the direct contact heat exchanger, and this is state number 9. So state number 9 here is the saturated vapor. Okay, so and then from state number 7 it will be flown to the other expansion valve, and then it's exit at state number 8, and then entering evaporator and back again to state number 1. So in case we want to compress the working fluid from state number 1 to the pressure level of state number 4 or number 5, and we only use one compressor, so it's mean the process line will follow this one, will follow this line. So let's go to point A here. But by applying an intercooling between these two compressors, then at the exit of the second compressor will be point 4. Okay, so it's mean in this case we will have less compression work. Okay, and the second one, what you can see in here is that at the entrance of the condenser, the temperature level will be 0.4 with this cooler. So this, from the thermodynamic perspective, we also lower the external irreversibility of the system, because the delta T between the working fluid inside the condenser and the one of the warm region is smaller. The next topic is absorption refrigeration. So this is a different type of refrigeration system. When we compare this absorption system with the standard vapor compression refrigeration system, there are two main difference here. First, that's in this absorption system, liquid working fluid is pumped, while in the standard compression refrigeration system, it is the vapor that is compressed. So this means that this absorption system will require a lower energy from outside. Why? Because pumping liquid requires much lower energy than compressing a vapor. Okay, and then the second one, some means must be introduced in absorption system to retrieve the refrigerant vapor from the liquid solution before the refrigerant enter the condenser. So we have a detailed explanation in the next slide. So it's mean for this absorption system to work properly, we need external heat supply, okay, to retrieve the refrigerant vapor from the liquid solution. So absorption refrigeration also require two working fluid, okay. For example, ammoniac and water, or maybe water and lithium bromide. So in standard vapor compression refrigeration system, we only need one working fluid. So in this absorption refrigeration system, we need two working fluid. So this is the schematic of the absorption refrigeration system. So let's start with the component on the left side. So in this case, we have condenser, we have expansion valve, we have evaporator. So this means that this is the refrigerant cycle. So pretty much the same as the standard vapor compression refrigeration system. And then in this absorption refrigeration, the compressor is replaced by this component. So you can see in here, this is used to replace the compressor component. So the first component here, what is called absorber. Okay, in the absorber, assuming that in this case we have ammoniac and water as the working fluid, in this absorber, ammoniac vapor coming from the evaporator is absorbed by the liquid water. So once again, on the left side we have ammoniac as the working fluid, so we have NH3 as the working fluid, and then on the right side we have water. Okay, so on the left side, the way condenser, expansion valve, evaporator works are the same as the one for the standard vapor compression refrigeration system. Okay, so let's start with the point number one. So in this case, ammoniac vapor coming from the evaporator. So it is at step number one. And then it flows into the absorber and then mix with water. Okay, because we have the water solution on the right side here. So inside the absorber, ammoniac mix with the liquid water, and then in this case the process of this mixing is an exothermic process. Therefore we need a cooling cooling liquid. In this case it is a cooling water to remove the heat generated during this mixing process. Okay, and then it exits the absorber at point A. Okay, at point A, and then in this case we have a strong solution. It's called strong because water contains a high concentration of ammonia. Okay, at the point A here, the phase is liquid, and then it is pumped to point B. Okay, to point B. So, but it's still a strong solution. So it means we have a high concentration of ammonia inside the water solution. And then the next component here, what is called a generator. So in the generator, heat transfer from a high temperature source drive the ammoniac vapor out of the solution. So once again, to separate this ammoniac from water solution, so we need an external heat. So this one. Why? Because this is a kind of the endothermic process to separate this ammoniac from the water solution. Therefore, we need a heat from the external. So, and then inside this generator, we will have a stream flow at point 2 here, which is mainly ammonia. So ideally it will be 100% ammonia, and then going to the condenser and so on. And then the water solution with less concentration of ammonia will be a flow to this path, and then through the valve back again to the absorber, and the working fluid through this valve, so from point C to point maybe D here, is the working fluid with less concentration of ammonia. That's why it's called weak solution. Okay, so just to make sure to differentiate between weak and strong. So on this line we have a strong solution. It means the water solution contains a high concentration of ammonia, and then entering the generator there will be a separation between the water solution and the ammonia. So at point 2 here we have almost 100% ammonia, and then at point C here we have less concentration of ammonia inside the water solution. So as I mentioned to you in the previous slide, we don't have a compressor here, And what we need to input here is the power required by the pump, which is much smaller than the power required by the compressor. And also we need to have this one, heat from the external source to separate ammonia from water solution. And then this absorption refrigeration system, it's still under development, and one of the modification found outside there is by having a heat exchanger between absorber and a generator. So this one is the additional component. So from the absorber we have a strong solution, and then it is pump, and then you can see in here, before it's enter the generator, they will get a heat transfer from the fluid that is flow back from the generator to the valve and back to the absorber. So a good thing of this modification is that we will need a less external heat here, because some of the heat has been supplied by the working fluid inside the heat exchanger. Okay, and then we also find frequently additional component here, which is called a rectifier. So the purpose of this rectifier is to trap any water that's go to this line, and then the water will be directed back to the absorber. So with this case, we will have a higher concentration of ammoniac when it enter the condenser. The next type of the refrigeration system is what is called a gas refrigeration system. So in this gas refrigeration system, there is no phase change throughout the cycles, and this gas refrigeration system can achieve very low temperature that can be used to liquefy air and other gases. And then for this gas refrigerant system, we use a reference cycle from the Brayton. So in this case, we reverse the Brayton power cycle for gas turbine cycle. This is the schematic of gas refrigeration system. They have four primary components. So turbine, and then heat exchanger. So this is the evaporator, and then compressor, and then heat exchanger. That's work as the condenser. So there will be a heat transfer from the region that we cool, or from the space. And then this is the compressor. So compressor will require a work, and then some of this work is provided by the turbine work. And then inside this heat exchanger, the heat is removed from the working fluid. And then on the right side is the TS diagram. So point 1 here is at the entrance of the compressor. It is compressed to point 2. So we assume here there is internal irreversibility inside the compressor. So you see there a dash line. And then inside the heat exchanger, so the condenser, the working fluid is cooled down, so at constant pressure, to point number 3. And then it's entered the turbine doing an expansion process. It goes to point number 4. So we assume there is internal irreversibility inside the turbine. And then inside the evaporator or heat exchanger, the state 4 is brought back to state number 1. And you can see in here there is two horizontal lines representing the TC. So this is the cold region temperature, and TH, so this is the warm region temperature. This is the analysis for gas refrigeration system. So for the work produced by the turbine, we have this formula. So this is H3 minus H4, and then the work required by the compressor, we have H2 minus H1. So you can see in here we maintain all number here positive. And then the refrigeration effect, so this is Q dot in, it is M dot time H1 minus H4. And then COP is what we gain over what we pay. So what we gain here is the Q dot in, and what we pay here is the compressor work minus the turbine work. Let's take a look at this simple example. Air enters the compressor of an ideal Brayton refrigeration cycle at 1 atmosphere and temperature of 480 degree Rankine with a volumetric flow rate of 50 cubic feet per second. If the compressor pressure ratio is 3 and the turbine inlet temperature is 540 degree Rankine, determine the net power input in BTU per minute. Okay, and then the next one is the refrigeration capacity. It is in BTU per minute. And the last one is the COP, so the coefficient of performance. Let's have a look on the solution of this example. So on the left side is the schematic of the system. So we have point 1 at the entrance of the compressor, and then the flow rate is given. So AV, so 50 cubic feet per second. T1 is 480 degree Rankine, and P1 is 1 atmosphere. And it's compressed inside the compressor, and then at the exit we have point 2S, and then at point 3, this is the entrance at the turbine, the temperature is given, so 540 degree Rankine. And on the right side is the TS diagram, so isentropic process between point 1 and point 2S, as well as the isentropic process between point 3 and point 4S. Therefore, they are connected by a straight vertical line, and no pressure drop inside the two heat exchangers. Therefore, P4S equal to P1 as well as P3 equal to P2S. And this is the engineering model or the assumption. So it's a control volume at steady state. And then the turbine and compressor processes are isentropic, so it's mean adiabatic, internal reversible. And then there are no pressure drop through the two heat exchanger. And then we can ignore the effect of kinetic and potential energy. And the working fluid is air and can be modeled as an ideal gas. The first step is fixing properties at each state. So we can start with state number 1. So this is at the entrance of the compressor. So temperature and pressure are given. So this is air, and it is a British unit. So we need to use table A22E. So go to table A22E, looking at the temperature at 480 degrees degree Rankine, you will get the enthalpy of 114.69 BTU per pound. And you also need PR1 here to help us determining the properties at state 2. PR1 is 0.9182. And then since the compressor process is isentropic, so it's mean we can use the pressure ratio and PR ratio correlation to get a PR2. Okay, so P2 over P1 is given in the problem statement, so this is 3, and then PR1 is 0.9182, so we get a PR2 of 2.755. And then you need to go back to table A22E, and for sure you need to do an interpolation to get what is the enthalpy at state 2S. And then for state number 3, the temperature is given, so 540 degree Rankine. Use the same table and to get the enthalpy at state 3 as well as the PR at state 3. So you will use this PR3 to determine the state, the properties at state number 4. So similarly, you will get PR4 from the correlation between the pressure ratio and PR ratio. So PR4 is 0.462. And then by doing the interpolation, you will get the enthalpy at state 4S of 94.1 BTU per pound. Okay, we have completed fixing the properties at each state. Then we can start answering the question. The first question is the net power input. So this is the compressor power minus the turbine power. This is the compressor power and this is the turbine power. So we need to get the m dot. What is given in the problem statement is A times V, so capital V, so this is volume. So A times V here is the volumetric rate, it is given in the problem. To get the m dot, we need to divide this A times V by the specific volume. So in this case, we can use step number 1 to get what is the specific volume. And the specific volume at point number 1 can be estimated by using the ideal gas equation of state. So this is the ideal gas equation of state. We can get V1 and then we can substitute V1 in the m dot equation by this term. So we have this one and then P1 is given, T1 is given, R with over bar here is the universal gas constant. So in British unit we have 1545, okay, and then m here is the molecular weight of air, so this is 28.97. so you just plug in all number here, so you will get the m dot of 248 pound per minute. And then we can plug in the number to get the net work from this gas refrigeration cycle of 1848 BTU per minute. The second question is the refrigeration capacity, so Q dot in. So this is dot time H1. So H1 here is at the exit of the evaporator minus H4S. So this is at the entrance of the evaporator. So we have all number here. You just need to plug in. You will get 5106 BTU per minute. The last question is the COP. So this is Q dot in over W dot cycle. So Q dot in, we got it from the answer of B, and then W dot cycle, we got it from the answer of A. So you will get a COP or beta of 2.76. Okay, the next example. So this is example 10.6 in the textbook. So in this case, we will reconsider the previous example. So example 10.5, so the one that we just discussed, but include in the analysis that the compressor and turbine each have an isentropic efficiency of 80%. Okay, so pretty much the same as the previous problem, but we have an internal irreversibility inside the compressor and turbine represented by this isentropic efficiency of 80%. The question is, what is the net power input, and then refrigeration capacity, and the last one is the COP of the system. This is the modified TS diagram to represent that there is internal irreversibility inside the compressor as well as the one inside the turbine. So you can see in here we have two dash line. The first one is the one that connect state 1 at the entrance of the compressor to state 2 at the exit of the compressor. And then we have state 3 here at the entrance of the turbine, and then at the exit of the turbine we have state 4 here. Okay, and then T1 is given, and then T3 is given, and then P1 is 1 atmosphere. And this is the engineering model. So control volume at steady state, and the compressor and turbine are adiabatic. Okay, you can see here that the compressor and turbine are still adiabatic, but they do have internal irreversibility. And the next one is that there are no pressure drop through the heat exchanger. And then we can ignore the effect of kinetic and potential energy. And the last assumption here is that the working fluid is air and it can be modeled as an ideal gas. The first question is the power input to the compressor and to the turbine to get the net power. So from the previous problem, we already got the power, the required power by the compressor. And then in this problem, the isentropic efficiency of the compressor is given 80%. To get the actual compressor work, so we just dividing the isentropic compressor work by the isentropic efficiency. So you will get the actual compressor work is 147 BTU per minute. Okay, and then you also get the turbine power here from the previous example. So it was the isentropic turbine power. To get the actual turbine power, you need to multiply. Okay, you need to multiply it by the turbine isentropic efficiency. Okay, so you will get the actual turbine power of 6936 BTU per minute. Then to get the net power input, you just subtract the compressor power by the turbine power. So the net power is 6211 BTU per minute. Okay, and then the next one, we need to calculate what is Q dot in. So Q dot in is m dot times H1 minus H4. So we got H1 from the previous example, but we need to get H4 here. Okay, so the turbine power is m dot here times H3 minus H4. So we already got turbine power from the answer of A. So in this case, we can calculate what is the enthalpy at point 4. So the turbine power, we got it from the answer of A, it is 6936. And then H3, we got it from the previous example because temperature is given. Then you will get H4 of 101.1 BTU per pound. So once we get H4, we can plug in H4 to this formula to get Q dot in. So Q dot in here is 3370 BTU per minute. And then the COP or beta is the ratio between Q dot in and W dot cycle. So you will get a beta of 0.543. So if you compare beta of this answer with the one from the previous example, this beta is much smaller. Why? Because we have internal irreversibility inside the compressor and the turbine. The next one is the modification of gas refrigerant system. In this case, we add a heat exchanger here that is placed between the compressor and the turbine. So we can start with point number 1. It is at the entrance of the compressor. So in the TS diagram, this is point number 1. And then the working fluid get compression. It goes to state number 2. Okay, and then there will be a heat removal from the working fluid, goes to the warm region that bring state 2 here to state A here. And the temperature at state here is higher than the temperature for the warm region. Okay, and then by adding this heat exchanger, we can further cool the state A here to state number 3. Okay, so instead of state A here is the final temperature before entering the turbine, we can apply the heat exchanger that can further cool working fluid from state A to state 3. Okay, so from state 3, it flows to the turbine going to state 4. So by having this additional heat exchanger, you can see in here that we can generate a lower refrigeration temperature, because now you have a T4 here instead of having T4 somewhere here. Okay, and the application of this modified gas turbine is on cooling the cabin in an aircraft. Next one is CO2 for automotive air conditioning. On the left side is showing the schematic of this CO2 air conditioning. So we have a compressor and then this is a condenser, and then point 3 here is the exit of the condenser. And then before it's enter the expansion valve, we have heat exchanger here that cool down this point 3 to point 4, and then the heat here is used to heat up the working fluid before it's enter the compressor. Therefore it will reduce the required compressor work. Okay, and for the CO2 working fluid, we have several points here that operates above the critical point, because the critical pressure and temperature is somewhere here. So this is state number 1 at the entrance of the compressor, and then state 2 is at the exit of the compressor. And then after cooling inside the condenser, the working fluid state is point 3. There'll be a further cooling inside the heat exchanger that bring it to state number 4. And then from 4 to 5, this is a throttling process. And then 5 to 6, this is a process inside the evaporator. And then from 6 to 1, this is the process inside the heat exchanger. So the working fluid get the heat from the other side that change or increase in temperature from T6 to T1. The last topic of this chapter is heat pump systems. The objective of a heat pump is to maintain the temperature within a dwelling or other building above the temperature of the surroundings, or to provide a heat transfer for certain industrial processes that occurs at elevated temperature. Left side here is the schematic of the heat pump cycle. So we have evaporator, compressor, condenser, and turbine. So if you compare this schematic with the one for the refrigeration system, they are exactly the same. What is the difference is that in this heat pump, we will utilize or we will use this Q dot out. Therefore, when we estimate the performance of the heat pump system, it is this Q out that will be calculated, or that is the parameter that will be compared with what we pay here. Okay, not Q dot in. Okay. So on the right side is the TS diagram. So on this ideal cycle, so we have two constant pressure processes. So it's from point 4 to point 1. So this is inside the evaporator, and from point 2 to point 3. This is inside the condenser. And then we have also two isentropic processes. So from point 1 to point 2, this is isentropic process inside the compressor. And point 3 to point 4, this is isentropic process inside the turbine. And then because this is ideal Carnot process that have two isentropic processes and two constant pressure processes, so we can use the area in this TS diagram to represent the amount of heat. So the coefficient of performance for this heat pump cycle, so in this case we use gamma here, it is the ratio between Q dot out, okay, Q dot out over M dot to the net work. So this is the work difference between the compressor and the turbine. So this is the area surrounded by point 2 AB32, okay, divided by area surrounded by point 1, 2, 3, 4, 1. Okay, so if I use this line, so this is the network. Okay, and then Q dot out over M dot here is this area. Okay, and then you can formulate these two area by TH times SA minus SB, and then the network here is TH minus TC times SA minus SB, and then we can simplify it to have gamma equal to TH over TH minus TC, equation 10.9. 9. And then, like in the vapor compression refrigeration system, we also have vapor compression heat pump. So it means the working fluid entering the compressor will be at least at the saturated vapor. And the feature here is showing the schematic of the heat pump to provide the heat inside the house. So the evaporator is at the outside of the house now, and then we have a compressor here, and then the working fluid is flow inside the house, and then we will have a condenser here, and there will be a heat transfer from the working fluid to the air inside the house, and then it's flow back through the expansion valve, and then we have point number 4 here, and then it will flow back to the evaporator. And equation 10.10 here is the COP of this heat pump. So this is the ratio between Q dot out over M dot over WC over M dot. So we don't have a turbine power here because the turbine is replaced by the expansion valve. And the reason why we replace the turbine by expansion valve is the same as when we talk about this similar case in the vapor compression refrigeration system. And you know your house has AC, or you have a refrigeration system during summer, and then during the winter you don't need to have a different system. You can use the existing system to provide the heat so that your house get a warm air. So this means that you only have a single system that can work either as the refrigeration system or the heat pump. So to enable this system switching, we have additional component, what is called here a reverse valve. So depending on the mode of the system, either the working fluid will flow following the solid black line here. So this means this is the heating mode. And then if we switch the valve, the direction of the flow will reverse, and then it will follow the it will follow the dash black line here, and this is in the cooling mode. So we still use same compressor, we still use the same expansion valve, but the two heat exchanger here will switch the role. Either at certain point they will serve as the evaporator, and at other point they might serve as the condenser. Let's take a look on this example. Refrigerant 134A is the working fluid in an electric power air source heat pump that maintains the inside temperature of a building at 22 degrees C for a week with the average outside temperature of 5 degrees C. So 5 degrees C here, it's around 40 degrees Fahrenheit. So it's about winter season. And then the saturated vapor enters the compressor at -8 degrees C and exits at 50 degrees C and 10 bar. Saturated liquid exits the condenser at 10 bar. The refrigerant mass flow rate is 0.2 kg per second for steady state operation. The first question is the compressor power in kilowatt, and then the second one is the isentropic compressor efficiency, and the next one is the heat transfer rate provided to the building in kilowatt. And then the next one is the coefficient of performance, and then the last question is the total cost of electricity in dollars for 80 hours of operation during that week, evaluating electricity at 15 cents per kilowatt hour. Let's take a look at the solution of this problem. This is the schematic of the system. We have a compressor, and then condenser, evaporator, and then expansion valve. And then the right side is the TS diagram. So point 2 is at the entrance of the compressor, and then it's supposed there is internal irreversibility inside the compressor. Therefore, we have a dash line connecting state 1 to state 2 here. And then state 3 is saturated liquid. This is at the entrance of the expansion valve. And then state 4 here is at the entrance of the evaporator. And this is the engineering model, pretty much the same as the one in the previous example. So it's control volume steady state, and then no pressure drop through the evaporator and condenser. And then the compressor operates adiabatically, and then the expansion through the valve is a throttling process. We can ignore the impact of the kinetic and potential energies. And then saturated vapor enter the compressor, this is state 1, and saturated liquid exit the condenser, so this is state number 3. And then for costing purposes, conditions provided are representative of the entire week of operation, and the value of electricity is 15 cents per kilowatt hours. I think you can open the CPS website to check whether this 15 cent is current price for electricity in San Antonio. The first step is fixing the properties for the principal states located on the accompanying schematic and TS diagram. So we have schematic at the bottom here along with the TS diagram. We have state number 1, and then state number 2, state number 3, and state number 4. State number 1, you can get the value from the table directly because temperature is given -8 degrees C and it is saturated vapor. So by using saturated temperature table, you should be able to get what is H and S. And then state number 2, I think pressure and temperature is given, and this is superheated. So you will use table A12 for this refrigerant 134A. Okay, so you will get H2, and then state 3, pressure is given 10 bar, and this is saturated liquid, so you will use saturated pressure table, table A11, to get H3, and then H4 equals to H3. So by following that step, you should be able to get the properties at each state. So in this table, so you have H1, H2 through H4. Then we can start answering the question. The first question is the compressor power. So this is W dot C equal to M dot times H2 minus H1. M dot is given in the example statement, so 0.2 kilogram per second, and then H2, H1 is coming from this table. So you will get the compressor power of 7.53 kilowatt. The second question is the isentropic efficiency of the compressor. So this is the ratio between the isentropic compressor work over the actual compressor work. So H2S minus H1 over H2 minus H1. So we have H1, we have H2 from the previous table. We need to get what is H2S. So H2S here is estimated based on the information of the entropy. So where S2S equals to S1 and pressure is 10 bar. So you need to do interpolation using table A12 to get H2S, and you will get H2S of 274.18 kilojoule per kilogram. So you will get compressor efficiency of 84%. The question number 3 in C, this says the heat transfer rate provided to the building. So this is Q dot out. So this is M dot times H2 minus H3. Okay, so you have all number, you just plug in all number to this equation, you will get Q dot out of 34.98 kilowatt. And then the heat pump coefficient of performance, so gamma, this is the ratio between Q dot out to WC. So you will get COP of 4.65. Okay. And then the last question is using the result from part A together with the given cost and data. So the data, I believe for 1 week it's operate 80 hours, and then the electricity cost is 15 cents per kilowatt hours. So this is the compressor work. So you will get the cost per week. So this is compressor power multiplied by the duration of operation, so 80 hours per week, and then multiplied by the cost of the electricity, 15 cents per kilowatt hour. So the operating cost per week, which is for propelling the compressor, this is $90.36. Okay, we have completed this topic. So to improve your proficiency on solving the problem related to refrigeration and heat pumps, I encourage you to solve the problem at the end of chapter 4 or chapter 10 in the textbooks.